Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. Let's continue our discussion on the method of weighted residuals. So, yesterday we talked about how we approximate the phi. Well, just to recall a few steps, is that in general we can put the problem in this manner. So, L phi plus f is equal to 0 in the domain omega, and m phi plus g is equal to 0 on gamma. So, this is the boundary condition. So, these are to be satisfied. So, what we are proposing is that phi will be approximated by phi hat, and where phi hat is going to satisfy the boundary condition a priori. So, that means that we choose phi hat so that the boundary conditions are satisfied by choosing in this manner. So, to start with, we choose phi hat as a summation of several functions here, known functions. Psi naught is a known function, as well as the set psi j is also a known function. And then there will be n terms here, and we have to systematically choose psi naught and psi j. The important point here is that the psi naught is chosen m psi naught plus g is equal to 0. So, that means that the psi naught satisfies the boundary condition as such, non-homogeneous part, whereas psi j, the set here for all j is equal to 1. So, the set psi j here, which is used in the summation here, is such that it will be satisfying the homogeneous part of this boundary condition. Okay. So, thus we have seen in the morning that by choosing psi naught and psi j in this manner, we are satisfying this identically. Okay. So, the boundary conditions are satisfied here completely, and then the other thing that is remaining is that how to make this phi hat satisfy this given boundary condition in omega itself, in the whole domain, everywhere. So, that what we are doing is that, since this phi hat substituted in this one is an approximation. So, since this is not an exact solution, so this is not equal to 0, and then it is some value we call it as residual. So, this we call it as error or residual. So, obviously this is non-zero in the domain. So, our endeavor is to make this as small as possible. So, by substituting this one here, so what we have is that by substituting, we can also substitute phi hat this one into this one, and then if you look at this one, substituting this one, so this is what we did. So, this is equal to L psi naught, right, plus L j L psi j plus f. So, this is as we have shown, and this as you can see here, this has undetermined coefficients ages, while the psi naught and psi j are assumed as per our method. So what is to be done? So to find out this ages, so there are n coefficients, so we need n equations. For that, what we are proposing is that, so this will be weighted against a known function here into r phi hat. So this residual, we will make it by weighting against wi. So this is what we discussed in the morning. So how to make this residual 0 is by the method something known as taking its projection. So in the morning we were talking about its analogy with respect to the vector algebra. So so this is nothing but this, we call it as inner product, but in the sense of vector algebra we call it as a simple dot product. So that means that the vector here and its projection on this quantity, just to recall, so this is similar. In the morning we did it. It's a little repetition of what we have done in the morning, but however, it's worth doing it. And so if you take it, taking similarity with vectors. So here this R with I is 0 and R with J is 0 and so another important thing which I would like to point out is that the product of this dot product or its projection on x-axis is 0 here, its projection on y-axis is 0 here, and its projection on z-axis is 0. So that means that, so if R is only 3-dimensional in nature, so if it is projection in all the 3 basic directions is 0, so this essentially implies R is identically 0, right? So this is what the vector algebra says. So what we need to appreciate here, that the projection of R in 3 directions x, y, z is 0. So it is also not necessary that they have to be only x, y, z directions. It can even be any 3 other unit vectors E1, E2, E3, and if we say that the projection of R on these unit vectors E1 and E2 and E3 is 0, then again the R will be identically 0. So what we are trying to say is that, so as long as the basic vectors E1, E2, E3 or x, y, z, so as long as they are independent in nature, in the sense that they do not depend on each other, so these 3 are going to span the whole space, either ijk or E1, E2, E3, or for that matter any other 3 vectors. A summation, a linear summation of those vectors, if they can span the whole vector space, and if we are making that R is 0 in each of these basic vectors, then R will be identically 0. Okay, so this is as far as vector algebra is concerned. As far as this is called a finite dimensional space. Okay, it can be extended to n, but still it's finite dimensional. So the same analogy will be applied to this functional space. So in this functional space, so this R is the error or residual, and then this R is taken as a product, is called an inner product, and is 0. So here this so that means that its component along Wi is 0, and then you can also extend it to I to 1 to n, or n being infinity. So that means that if it's the projection on all these basic unit functions here is 0, so then we can say R is 0. So there are two important criteria here, is that so important considerations are there are two important considerations here. So here this psi j, so here phi hat has been expressed as psi naught plus aj psi j. So the set here psi j's, so this set of functions called basis functions. So that means that the combination, a linear combination of these functions psi j's is going to represent any function in the space. So which means that it's a complete set and also a linear combination of will be able to represent any function. To any. So here we are having the value n, finite number of functions, but as the number n increases to infinity, so that means that these set psi j linear sum will be able to represent any function, okay, to any desired accuracy. So whatever accuracy you desire, so you will be able to achieve that by taking this n as high as possible, and any function here will be able to represent, because at this moment we do not know what is the function, and so we do not know, given a problem we do not know what kind of function it is, and we do not know what to use. So but however, what we can say is that the set psi j is a complete set, and any function will be able to be represented by a linear summation in that domain. Okay, so this is one, right? So this is the, so we know that here that such basis functions are something like the Taylor series. The terms are 1 x squared. So that means that this is the sizes. So a combination, linear combination of this one will be able to represent any function in one dimension. It can also be converted to Fourier series also. So where we have terms like 1 sin x cos x sin 2x cos 2x. And of course, you can also put L and all that, x by L, 2 pi x by L. And essentially what we are saying is that this kind of trigonometric terms, a linear combination will be able to represent any function in that domain in one dimension. It can also be converted to two dimensions. So like this, we have a legendary polynomials, okay, legendary polynomials, and so on and so on. So we have these kind of basis functions have been defined, okay. So that means that whenever you choose a phi hat here, so the terms here should be a complete set, and it better be polynomial terms in a systematic manner. And why do I call systematic manner? So that means that you choose 1x, x square, x cube, x4 in a systematic manner. So what I mean is that, so you choosing 1x and leaving x square and going for x cube, x to the power of 5, so will not be able to achieve the desired accuracy because the terms are not chosen systematically. So they have to be chosen in an exhaustive manner from the lowest order to the highest order. So similarly here, so you're not expected to leave any terms here. Then what happens if you leave out one term is that the error will be of that term or nature of that term, and then you will not be able to achieve any accuracy. All right. So this is about the unknown function phi hat. So the same thing is true. So this is about phi. So then choosing the weighting functions, wi's has the same restriction. In the sense that the set wi's should also be a complete set, just like here, okay, and you should use them in an exhaustive manner, in a systematic manner. So whenever you choose here, so here you choose a complete set starting like in Taylor series terms, 1x x square, or even this one. There is an interesting thing here that the terms which you use for the representation of psi, okay, are the terms which you use for weighting functions. Do they have to be same or can they be different? So the fundamental requirement here, as far as this method is concerned, is only that Ij's have to be complete set as well as wi's has to be complete set. It's not necessary that it has to be same set. Okay, so that's what brings us something known as the terminology. That's a basic set of equations. So let it be there. So what we are saying here is that wi's have to be also have to be a complete set. Okay. So if wi's are the same as chi's, so there's is as, okay, or wi's different set. So these are going to lead to two different methods. So if they are same, then we call it as Galerkin method, and if they are different, then it's called a Petro-Galerkin. Petro-Galerkin method. Okay, so these are very popular methods. Galerkin method is very popular. Why? Because we are going to use the same set as that of psi here, and so that way the method slightly becomes simpler. That's number one. Okay, even the derivation of various terms which are involved there will become simpler. That's number one. Number two is that some of the equations which we derive here, so the linear algebraic equations, will turn out to be simpler in the sense that the matrix which we define as K may turn out to be symmetric also. This has tremendous advantage from the computational point of view. Whereas this Petro-Galerkin is very general, and then in certain situations, like in fluid mechanics or something like that, so there it is better that we use different sets of these W's and Psi's. Okay, but however, in our approach, we are going to encounter the Galerkin method. So it's in general it is a Galerkin. So if you use this method, so people call it as Galerkin weighted residual method. So Galerkin weighted residual method means that this is the method which we follow where Wi's are the same as psi i's. Okay, so that's what it is. Okay, so there are a few associated things like associated things are point collocation, subdomain collocation, or least square they all come under the same class of this method of weighted results. So let me explain each one of them. What is point collocation method? So the point collocation method here is that I'm not going to go deep into that, which you can derive yourself, but since it's important here that I tell them. So what is point collocation method? So the point collocation method is in the domain here where we have defined our phi as L phi plus f. Maybe we'll put hat if you want. So phi hat, of course, has all those n terms, psi naught, psi 1 to psi n. And then if you want to get the n equations, so one way of doing this method, so the very age-old method, so this r phi hat has to be 0 everywhere, but since we have only n terms here, so what we choose here, that we choose points 1, 2, 3, and so on up to n well-spaced points, and then say this is x1 by 1, x2 by 2, x3 by 3, and all the way to xn, yn. So we choose equispaced thing, and then what we say is that this residual is 0. So residual is 0 at finite locations, at finite points. Say P1 up to Pn. So we are only saying that it's not completely zero over the whole domain, which is not possible for us. And only thing which we are saying here is that this R phi hat is zero only at certain n locations. So in the sense that this L phi hat plus F, which we write as, so that means that this is 0 at Pi. Let us say if this is 0 at Pi, so let us say what we mean at Pi, if you call it as xi, yi. So that means that this residual is made 0 at xi, yi to get the ith equation. So this is ith equation. So you can get n number of equations by choosing this Pi to be P1, P2, P3. So you will get n equations by making residual 0, 0 at finite at these points. Okay. So that way, this is called a point collocation method. So what is this? Can this be considered as a method of weighted residual? Okay. So if this is considered as a method of weighted residual, so what is the weighting function which need to be specified here? So what is that? Here we are saying is that we are saying that so if this is the weighted residual statement, then how can this be equal to this statement? So that is possible by choosing here the Wi. So by choosing this Wi here as Dirac delta function. So if you choose Wi as Dirac so which we call it as delta xi. So this is called a Dirac delta function. So let's say in one dimension, so just if it is one dimension, in one dimension, so here the function is like this. So the function is a point function like this one, where at x is equal to xi, it is going to shoot to an infinite value. And what it is that the integral over so the integral over the domain, if a is less than xi, okay. So this is one property it has. And so similarly, we have here multiplying this with some function x here. So it can be shown that if it is like this, so this is fxi. So if you multiply with the Dirac delta function, any function, and then if you integrate it, then this has the property that this whole thing, now this is infinity at x is equal to xi, so the whole thing will be just simply fxi. So that's what exactly is what's happening. So if you write this as Dirac delta function, and then this is this part here, And then if you are integrating it over the whole domain, so the whole thing will be nothing but the whole thing evaluated at P is equal to Pi. Okay. So that way we have shown that point collocation method is also one of the weighted residual methods. So similarly, subdomain is nothing but over smaller subdomains. And I think I'll leave this least square method to you, and where the error here in the least square method, what we have, I'll just mention that here. So the least square method, so the residual here is written as whatever you have here and square it. So this is the error, call it square error. And so this is obviously pi hat being non-zero here. I mean, this residual being non-zero in the domain. So you have a positive value. So this here, dot, yeah, this is the, let's call this as error. So if you differentiate it with respect to each of these coefficients, okay, and then try to minimize this one. So then also this, a part of this comes to the front, and then that will be the weighted function. So these are all various things, but actually that Galeckin weighted residual method is the most popular. These are some offshoots which have been in existence. So that means that the many methods can be come under the class of method of weighted residual. Okay, I think we'll stop here, and then we'll continue with an example and followed by many other intricate details of this method of weighted residual. Bye.